Hi, my name is Amr Dar, and my project was on collective graphical models. So there are a growing number of applications, especially in the social sciences, where data about individuals are not available, but aggregate population level count data is. For example, suppose we have an interest in understanding the relationship between education, sex, and housing among individuals in America. But the problem is the US Census only releases count data for privacy reasons. Now, suppose we'd like to study bird migration patterns, but we cannot track the individual birds, and can only collect count data like the number of birds we see at a particular location and time. Okay? So these two examples kind of suggest that the need for probabilistic models that account for observed count data, even though we're interested in trends at the individual level. Okay? So some notation. Now consider a graphical model defined on the triangulated graph G with discrete random variable set right here and a max click set C. Okay? Now each xi is in the domain 1 to r, okay, where I is a subset of v, and little bold-faced x is a joint setting for these random variables. And for any subset of the node set, little x sub a is a subvector of x. And we assume that for any joint setting of these random variables, the probability is greater than 0 for all x. We call this model the individual graphical model. Now suppose we've drawn a sample of NIID random vectors from this individual graphical model. Okay? We can define contingency tables over our sample of NIID vectors. Okay? So a contingency table little n is a vector with entries denoted right here that actually count the number of times each configuration I in the domain appears in the sample. Okay? And we'll use elements or indices like I to index the contingency tables n. And we'll call I sub a the corresponding subvector corresponding to some particular subset A of V. Okay? So by using I sub A, we can actually define subtables, N sub A, which are subtables of our full contingency table over all the nodes. Okay? And is denoted right here. It's counting all the possible configurations of the nodes in subset A. Now our observation model is as follows. Suppose we have our sample of size n from the individual model, and it's assumed to be unobserved, just like in the real world. Now instead, we observe noisy subtables, YD we call them, which is the vector of all possible tables YD in the collection of observed subsets of V. Okay, so we observe some sets of nodes. Okay, and for all possible observed subsets, there's always a max click such that D is a subset of the max click. Okay, so these observed subsets are always a subset of a bigger max click. Now each table entry in these YD vectors, or tables, each table entry YD sub ID, conditional on the true entry we don't see, is distributed Poisson. Okay, so there's Poisson likelihoods for each table entry. Now the collective graphical model distribution. Okay, so if we want to fit or learn the individual model from aggregate data, we only need to do inference on the sufficient statistics of that model. Okay, in our case, it's the set of contingency tables over our max click set C. Okay? Now, what is the probability distribution of our sufficient statistics is given in this following line right here. Okay? Subject to some consistency constraints, which essentially make sure that the set of all our contingency tables over our max click set actually is form valid contingency tables over our graph. Now, why do we want to do inference on this our NC, the set of all contingency tables over our clicks, given our data, observed data? Well, we have this procedure called the EM algorithm, and it's an iterative procedure that attempts to find the MLEs of parameters in models of missing data. And remember, our individual model, we don't actually observe any data. We observe these noisy subtables, right? So, because we don't observe data from that model directly, we can maybe apply the EM algorithm here. Now, in this procedure, there's a step called the E step, where we need to calculate expectations of the form, posterior expectations, NC given YD. Okay? So if we can somehow approximate these expectations by doing inference on the posterior probability distribution, then we can actually learn the individual model parameters. Okay? So basically, the rest of this presentation will be talking about how to do inference on the posterior probability distribution. Now I say here we're going to talk about two approximate inference methods. We're only going to talk about one, Metropolis-Hastings sampling. And the reason it's approximate inference is because exact inference on this posterior distribution is computationally infeasible. the state space of these contingency tables is way too large to do exact inference on. So it's entirely too slow. Okay, so we're going to talk about Metropolis-Hastings sampling. Okay. So a brief overview of the algorithm. Now suppose we have a univariate random variable x with some distribution that's either discrete or continuous, doesn't matter, and it's difficult to sample from. We can't sample from it directly. Okay, the algorithm says start with some initial value of that random variable, let's say x naught, and then choose a proposal distribution that can actually move from that x naught to a new x. Okay, so we should be able to sample any x in its domain with some positive probability. So once you choose that proposal distribution, simulate a new value of x, call the candidate value x naught star maybe, and then compute this acceptance probability, which is defined right here. Okay. Now you can accept the candidate sample x naught star with the probability you calculated above. Okay. Now repeat these steps over and over again with a new initial value of x naught star if you accepted the sample. Otherwise, use that previous initial value of x naught. And you'll keep on doing this over and over again until you generate enough accepted samples of x such that you're happy or you're done with the procedure. Okay. Now, actually sampling from this algorithm will provide you with approximate independent samples of x, the random variable x, in the limit. So as you run this procedure for many, many iterations. Okay. Now note that we can actually sample for any distribution that we know in closed form up to a normalizing constant, because the normalizing constant will actually divide out when you calculate the acceptance probability. So it doesn't actually even matter. Okay? So this procedure will generalize to sampling from multivariate distributions, and we can actually use it to sample from our posterior of interest, which is NC given YD. Right? So let's talk about Metropolis-Hastings sampling in our procedure. Okay? So we'll express the candidate values of our contingency tables NC as NC star, which equals to the old value that we had, NC, plus some shift, which is delta times Z prime. Now what are both of those values? The Z prime is a vector with the same length as our contingency table, consisting of positive or negative integers, and then delta is a positive or negative integer, indicating how far to move our contingency table in the direction of Z prime. Okay. Now the authors of this original paper that I read pick a Z prime from a set of moves called a Markov basis, where each possible move has two positive entries of 1, two negative entries of -1, and the rest equal to 0. Now this set of moves of Z prime allow for efficient calculation of our essentially a new set of tables, NC star. Okay. Now delta we pick from the following distribution right here, okay, where delta can be any integer that preserves the non-negativity of the new proposal NC star, and we've already sampled Z prime from before. So you do Z prime first and then you do delta. And so we can actually write this out as explicitly as a function of delta, because this looks exactly like a posterior distribution, but just not for NC, but the shifted one. Okay. Now, the distribution for delta is log concave, which allows for efficient sampling of delta, okay, using rejection sampling techniques. Now, there is a dilemma that states running a Metropolis-Hastings algorithm for this R posterior by proposing moves that we just discussed will actually correctly sample from the posterior in the limit. Okay. Now, because we chose delta according to this posterior looking probability, the Metropolis-Hastings sampler will always accept every proposal we pick with probability 1. Okay. And simulation results actually show that the sampler is faster than exact inference procedures, although it does require many initial burden iterations until we can actually do sampling that's approximately correctly from the posterior. Okay. So in conclusion, in situations where data about individuals are not available, but aggregate count data are, we can actually learn the individual level model parameters by doing inference on this collective graphical model, which is essentially the model over the sufficient statistics. Okay? Now, by using the Metropolis-Hastings algorithm to sample values from a posterior distribution, we can actually empirically estimate the expectation of a posterior, which are actually quantities we need for the E step within an EM algorithm. And as we discussed before, the EM algorithm will actually help you learn these individual model parameters. Okay? And the reason, of course, again, the reason why we had to do approximate inference was because exact inference was not computationally feasible due to the large state space of the collective graphical model. And unfortunately, I did not have time to talk about map estimation, but I hope you enjoyed the presentation, and thank you very much for your time.